Okay, now we consider an important result in the spectral theory of linear operators called the Gelfand theorem. So we first start with the definition of resolvent. So we consider a resolvent set. As we said, the resolvent set, rho for a closed linear operator T, the resolvent set is the set of complex numbers such that lambda I minus T is a bijection. Okay, so it is a bijection, and we show that in this case it will be also linear, bounded linear. Okay, and the resolvent is defined to be this. So let X be a Banach space. Be a Banach space. T is a closed, from X to X, is a closed linear operator. Then the resolvent, which we denote by RT. R means resolvent. T means that it's for this linear closed linear operator T. It is a mapping from the resolvent set. I should say 0T to the set of linear transformations. Okay, and how this is defined is mapping any lambda in this, which is, this is the subset of complex plane, maps to lambda I minus T inverse. Okay, we know that if lambda is from the resolvent set, then this one is in here. Okay, so that's how we define the resolvent. Okay, so a simple result or lemma, say, is this. Suppose that T, so the T is not directly related to this T here, just in general, if we have a bounded linear transformation from X to itself, and also the norm of T is less than 1, then we know that in this case, I minus T is invertible. Okay, and it is a mapping in our X. And what we're trying to show here is that we can estimate the norm of the inverse of I minus T. And this is bounded about by 1 over 1 minus the norm of T. Okay, so this part is what we have shown before, and then we just need to show the second part. Well, to show the second part, let's think about, let's do this. For any y in X, because I minus T is invertible, so we know we let, say, X be the inverse of that, I minus T inverse of Y. Okay, then we know, we'll look at the norm of Y. It is equal to the norm of I minus T applied to X. Right, this is how we define this X. Then this is just X minus Tx. And by triangle inequality, this is greater than or equal to the norm of X minus the norm of Tx. But remember that the Tx has a norm less than or equal to the norm of this 2. Okay, the norm of T and the norm of X. So that's why this is a bigger than or equal to the norm of X minus, because you're subtracting something even larger, so you get a smaller value. And this is equal to 1 minus the norm of T times norm of X. And we know that this is something positive, because the norm of T is smaller than 1. And from here, we can see that we'll apply I minus So I minus t to any y, I minus t inverse to any y. I know that this, according to our notation, this is just x. Okay, and this, as we showed in the first line, this is less than or equal to the norm of y divided by 1 minus norm of t. And this implies that the norm of I minus t, since the y is arbitrary, so the norm of the inverse of I minus t is less than or equal to that. Right? That's what we know from here. Okay, so that's how it's a very simple lemma, and there are other ways to prove this. For example, we know that if t has a norm less than 1, then we can consider the Newman series of this. We know that it's just the sum of, say, tk. K is from 0 to infinity. And then we know that the norm of I minus t inverse is going to be equal to the norm of that, tk. And this is less than the norm of tk. Right? And this is further, this is by triangle inequality. And then further, we know that this is less than or equal to the norm of t to the power k. K is from 0 to infinity. And we know that this is a geometric sequence since this is a fixed number that is less than 1. Okay, so that's why this is just equal to 1 over 1 minus norm of t. So this is another way to show this. Okay, so that's one thing we know. And from this, we can get a corollary, which says that remember that we can decompose the C into, this is a resolvent, then the point spectrum, which contains all the eigenvalues, and then the continuous spectrum, and then the residual spectrum, right? So what we're going to show later is that, at least for the corollary right now, is that this is open set. We can show that this is open. So this, which is the spectrum of T, will be closed, right? Because the complement is open. We can show that. And we can also show that the sigma T is non-empty later on. Okay, we'll show that sigma T is, the spectrum is non-empty if T is the bounded linear operator. And we can show that, we can show that sigma T is non-empty if T is a bounded linear operator. We can also show that sigma T is bounded. Okay, and yeah, we'll talk about that soon later. But this is how we're going to do. We're going to make a more study some properties of this decomposition or some components of this decomposition. So the first one I'm going to give here is that the resolvent is open set. Okay, again, let the X is a Banach space. This is a Banach space. T is from X to X, which is closed, linear, and we're going to claim that this resolvent is open in C. Okay, to prove it's open, we just need to show that every point is interior point. Okay, so let's say we start with some arbitrary point, lambda naught, in the resolvent. Then we know that it's in the resolvent, that means the resolvent is in the resolvent set. So the resolvent is a bounded linear transformation or bounded linear operator. Okay, and then let's say we make some slight change of this. Say if I have a lambda that is pretty close to lambda 0, then lambda, the resolvent at lambda is equal to lambda minus lambda naught I plus lambda naught I minus t. So I just add and subtract the lambda naught I. Okay, and then because I know this is invertible, so I can extract this term, which will be lambda naught minus I times the inside. I will have lambda minus lambda naught times lambda naught I minus t inverse. We know that this exists, right? then plus identity. Okay, so now let's see, can we bound this right-hand side? Let's think in this way. Say this is I plus this. So if this thing has a norm less than 1, then I know that this one is invertible, right? So if it's I plus t or I minus t, if the norm of t is less than 1, then I know that this exists, right? So I just need to make sure that is the case. So if, say, lambda minus lambda naught is smaller than 1 over the norm of the resolvent at lambda naught, which is this, then apparently when lambda minus lambda naught less than times so we can take the norm of this, just this will be less than 1. Right? The point is that right now this whole thing will be invertible. So let's call it, say, u. So if this is the case, then the u, which is defined to be I plus lambda minus lambda naught minus I minus t inverse, is invertible. Okay, and then we know that this is invertible as well because lambda naught is in the resolvent set. So this is also invertible. So if both are invertible, then the product should be invertible. So the lambda I minus t, which is equal to lambda 0 I minus t times u, is invertible. Okay, it's invertible. And the inverse, apparently that's the inverse, just u inverse times lambda naught I minus t inverse. So that means the resolvent at lambda is just equal to u minus u inverse times the resolvent as lambda naught. But the key is that for this to happen, we just need this. So as you can see, this is the bounded value, right? So this right-hand side is a positive number. So as long as my lambda is not so far from lambda naught, the radius is this, then it's guaranteed that the resolvent of lambda, which is the inverse of this thing here, exists. Right? So it's like in the complex domain, this is the C, so this is lambda 0, and I know that in the neighborhood of that, every point in the neighborhood will be will be also inside the resolvent set because the resolvent exists. Okay, so that's why this set is open. Okay. Another fact about resolvent identity. So there's we are talking about the first resolvent identity, but there's also others. Second one, but we're not using that now. Identity. So it gives out a very simple relationship between the resolvents at two different points. So say let lambda mu both in the resolvent set, then the resolvent of at lambda minus the resolvent at mu is equal to mu minus lambda times the resolvent at lambda times the resolvent at mu. Okay, so we're going to use this result several times later. So let's prove it. This proof is pretty easy. Let's just look at RT lambda. This by definition is lambda I minus T inverse. We know that this exists since lambda is in the resolvent set. And we can multiply the resolvent at mu, then I'll multiply the inverse of the resolvent at mu, and then the resolvent at mu, right? Because these last two just cancel out. And the inverse exists again because a mu is also in the resolvent set. So now I'm going to make a slight change of the middle term, which gives us the mu minus lambda times I plus I lambda I minus t. And again, this is by just adding lambda and then subtract it. I minus t inverse. Okay, and then this, as you can see, I'm going to put this, and then this together, because this is the middle term. So I can put this together, and then this together. For the first one, I'm going to get just some scalar, right? So I have the mu minus lambda times lambda I minus t inverse times mu I minus t inverse. And for the second combination, this 3, I can see that these two cancels. So I only have the last one left, which is this. Okay, so this, if I write it using the notation of the resolvent, this is just that plus RT of mu. And by subtracting this on both sides, I will get that one. Okay, that's the first resolvent identity. Okay, very simple relation. And then we're going to prove the continuity and actually the differentiability of the resolvent. Okay, it says that the resolvent RT, we know that it's a mapping from the resolvent set to Lx, is analytic. Okay, remember the analytic, obviously what that means. Remember this is in C. Okay, so analytic means that it is differentiable at every point. Okay, so let's see how to show this. We first want to show the resolvent is continuous, and then we show that it's differentiable. Okay, let lambda 0 or lambda naught is in the resolvent. Okay, then remember that as long as how should I say this? Because this is the open, rho t is open, so in the neighborhood of lambda 0, we know that it is also, so for this is lambda naught. So since it's open, I know that in the neighborhood of those this lambda naught, all the points are in the resolvent set, right? Because this is like, for example, this is rho t. Okay, so I won't care about the neighborhood of this lambda naught. And then we say that as long as lambda is close to lambda 0 enough, it's close enough, then we have a bound for that. So let's say if lambda minus lambda naught is smaller than 1 over, what do we know is that if this is less than I minus lambda I minus t inverse, if this is the case, then that's actually the ball here, right? The radius is that. But let me make it even smaller. So here, this inside here is just a resolvent, as you can see, at the lambda naught. Right, more clearly. Lambda naught I minus t inverse. Okay, if this is the case, we can see that with the resolvent, we know that this is this lambda is also in the resolvent set because it's in somewhere in here. Okay, and the norm of that is equal to, remember how we proved this? this is like my lambda. So this is my lambda. This is my lambda naught. So I take the norm of the inverse. It will be the, say this. You take the norm of this inverse. It will be the norm of this, bounded by about by norm of this times the norm of this. Okay. So to remember that u is this thing right here. Okay. So that's what I'm going to have. So that's the resolvent. It's going to be bounded about by resolvent lambda 0 times the u inverse. The u inverse is this, I plus lambda minus lambda naught I minus t inverse, this inverse. Okay, so I'm going to give an estimate of the last one here. So what is the inverse of this? So I'm going to call this, or negative of this, to be t. Okay, so let's say this is negative t. Okay, then I'll have I minus t inverse absolute value. And I know that this is bounded by 1 minus, if, I should say, remember the previous lemma, I'm going to call this thing minus t. So this last one here is just I minus t inverse. And I know that if the t has a norm less than 1, then this one here is less than or equal to 1 over 1 minus the norm of t. Okay, so now let's see how do we can we guarantee that? Because I asked my lambda to be so close to lambda naught such that this holds, so I can see that the lambda minus lambda naught times lambda naught I minus t inverse, which is this term, or the negative t. So this t will be equal to negative of this, but this is less than 1/2, as I require lambda to be very close to lambda 0. Right? As you can see. Right? If I like, it's just less than equal to lambda minus lambda naught times the norm of the resolvent. And I know that this one is less than 1/2 of this, 1 over 2 times that. So this whole thing is less than 1 over 2. Okay, so that's what the t is. I know that t is less than, has a norm less than 1/2. So the 1 minus norm of t will be greater than or equal to 1/2. The 1 over 1 minus the norm of t will be less than or equal to 2. So that means this whole thing here will be less than or equal to 2. Okay, and that's why this is less than or equal to 2 times RT of lambda naught. Okay, now we are ready to show that the resolvent is continuous at lambda, because by the first resolvent identity, we know that we know that RT lambda minus RT lambda naught, this is like lambda and mu, is equal to lambda minus lambda naught minus lambda times RT lambda naught RT this lambda, which one goes first? Lambda one goes first. Okay, so it's lambda, but it doesn't matter later on because we're going to separate them. It will be this. Okay, so then we take the norm on both sides. I'll have this is equal to this. I had double of this, so this is not here. Yeah, this is not here. So here I will get this is less than or equal to RT lambda norm and RT lambda naught norm times lambda minus lambda 0. Okay, I put a negative sign inside, doesn't matter. And I know that this is less than or equal to 2 times RT lambda naught. So that's why the whole thing will be less than or equal to 2 times RT lambda naught square times lambda minus lambda naught. And as you can see, this is independent of lambda. So I show that when the lambda is close to lambda 0, close enough, then this is bounded by that. So when lambda goes to lambda 0, the left-hand side goes to 0. So that's why we say that the resolvent is continuous at lambda naught. And because lambda naught is an arbitrary point from the resolvent set, so that's why the RT is continuous on the row of T. Okay, that's continuity. And then we need to show the differentiability. So to show the differentiability, remember that right now we have the resolvent is a mapping from row of T to Lx, and this is in C. So what do we define by continuity is that if you have some lambda 0 differentiability, if you have a lambda naught, which is here, then it doesn't matter how the lambda gets to. It doesn't matter how lambda gets to the lambda 0. You need to show that the limit exists. Okay, which means that you need to consider about the RT of lambda minus RT of lambda naught divided by lambda minus lambda naught, where lambda goes to lambda 0 anyway. You need to show that this limit exists, and it's the same. Okay, and we can show that because of the first resolvent identity. This is we have to use that. So maybe just look at this. So you just like this is lambda. They have lambda naught here. So then you just need to divide lambda minus lambda naught minus lambda. Divide this, and then you have the right side. So that's just equal to the inside of the limit is just equal to negative of R of lambda naught times R of, I think, lambda times RT of lambda naught. Okay, but it doesn't matter because I know that when lambda goes to lambda naught, this converges to the resolvent at lambda naught, as we showed the continuity in the first part. So this is nothing but just a negative of RT lambda naught square. Okay, just apply it twice. Okay, and it doesn't matter how lambda converges to lambda naught. I also have this. So that means the resolvent is continuous. Is differentiable at lambda naught. But this is the complex. It's defined on the complex domain. So the differentiability means analyticity, right? Means that it's an analytic function. So if you know that this is a result from complex analysis, the function is differentiable, means that it's analytic. So what do we mean by analytic? It means that for any point, it can be for any lambda 0. If we say that RT is analytic at x naught, it doesn't have to be defined on the complex domain. When we refer analyticity, it means that the RT of x naught plus h can be written as sum of something about x naught. I'll say ck of x naught times h to the power k. K is from 0 to infinity. If you can show that this can be written as a power series in this way, and it's convergent power series in this way, then we say that the RT is say analytic at the point x naught. It's just that for complex value case, as long as you can show that the RT is differentiable, then you can claim this. Okay, that's the result from complex analysis. But we're going to just use that fact here. So you can also see this by directly calling the definition for analyticity. You can try to show that, say for example, right here, I'm going to have the lambda 0, say lambda minus h. And by definition, that just means the lambda 0 minus h I plus or minus t inverse, right? That's the definition. Let's see if it can be expanded in a power series. And if we can, that's another way to show that it's analytic at the point x0. Okay, and that is actually true because we have this. Then let's say we we can extract. So I have this lambda naught minus t part minus hi, right? This thing inverse. And I extract this first term, so I have lambda 0 minus t times I minus h times lambda naught I minus t. Okay, and I'm going to apply the inverse to this. Okay, so now when h is small enough, I know this thing here is invertible. Okay, so let's just choose the h small enough, and this is the same thing. If you can show that this expansion or this power series converge for any h in the neighborhood of x0, in the neighborhood of 0, then it is called analytic. And that's the thing we're going to show here. So the h, as you can see, h just need to be less than 1 over the norm of h0. Oh, sorry, this is the inverse. h0 I minus t inverse. Okay, so if h satisfies that, then I know this is invertible. And it's not just invertible. We know the inverse, what the inverse is. Let me write it out first. Times lambda, this is the inverse, lambda naught I minus t inverse. Okay, I'm not just I know that this is like I have the I minus t. I know that it can be written as sum 0 to infinity for t to the power k, right? When the t has a normal less than 1. And this will be my t now. Okay, and so I can rewrite this as sum k from 0 to infinity of h lambda 0 I minus t inverse to the power k, then lambda 0 I minus t inverse. Okay, and remember that this whole thing is just the resolvent at lambda naught, and this whole thing here is the resolvent at lambda naught. And this h is just some constant scalar floating around, so it's just a sum 0 infinity. And you can see the resolvent we're taking k plus 1 power, and then we'll have the h to the power k. So that's indeed a power series. Okay, this is indeed a power series, and then we know that this is convergent because of this power. This one has is going to be convergent. Okay, so that's the power series representation, and we know that you can also show the analyticity in this way. Okay, now continue doing so. We remember that we want to show that the spectrum is non-empty. Okay, how do we do that? The claim is that we need the t to be a linear transformation. So if t is a linear transformation, a bounded linear transformation, then we can claim that sigma t is non-empty. Okay, it is to be bounded, not just closed. Okay, let's prove this by contradiction. Remember that the C is decomposed into rho t and sigma t, and sigma t contains all those three parts. But if this is the empty set, then it just means that this is the whole C. Okay, so if not, then the rho t is the whole C, entire C. And we know that this RT is analytic and that means the RT, the resolvent from this is analytical everywhere. It's analytical everywhere, right? Okay, so first I'm going to show that this RT is bounded. Okay, how do I show that? So now this is the whole complex plane. And let's say I have some radius here. Let's say this is the norm of t. So the radius is norm of t. So as long I have some lambda naught, which is bigger than the radius of t, say I have here, this is my lambda naught. So here, this point here is t, norm of t, and this is lambda naught. Then you can see for any lambda whose modulus is greater than or equal to lambda naught, and that will be greater than the norm of t, we know this lambda I minus t this can be written as lambda times I minus lambda t. And because lambda is large, it's even bigger than the norm of t. So I know that the norm of t over lambda, which is the norm of t over the modulo of lambda, which will be less than 1. So that's why I know this thing will be invertible. I know this will be invertible. Right? So this will be just equal to 1 over lambda. Let's say the inverse of this is equal to the inverse of this is equal to 1 over lambda times I minus t over lambda inverse. Okay, I know that is invertible. So it's invertible, then I can see we know lambda I minus t inverse exists, and this is in our linear functional. So this also means lambda is in. I should say that's always true. So this means that the resolvent at lambda, which is exactly this one here, is going to be equal to the resolvent. I just copy that times I minus t over lambda. Sorry, inverse, and this is also inverse. So this thing here is equal to 1 over the absolute value or the modulo of this lambda times the norm of this part. But I know that norm of this is less than or equal to 1 over 1 minus the norm of this. Right? This is what we showed before. So this is going to be 1 over 1 minus the norm of t over lambda. And now I can put lambda together, to the denominator together. That will be just the norm of lambda minus norm of t. 1 is on the numerator. Okay? And this, because the lambda is bigger than that, so this is going to be less than or equal to 1 over lambda naught minus t. But this denominator is a positive fixed number. So this is a finite number. Okay? So this means that the resolvent is bounded by this quantity here when it is outside of this radius with the of this ball with the radius lambda naught. And inside, so outside of this, it is bounded by this quantity. Inside, because this function Rt, the resolvent is a continuous function. Now, this is just a compact domain. A continuous function defined on a complex domain must have reached its maximum and minimum. So that means inside this is also bounded. And this implies that the Rt is bounded in the whole domain, in the whole complex plane. Okay? So RT is bounded outside, and RT is continuous in this ball centered at 0 with the radius lambda naught. And this is a closed ball in C. Okay, it's continuous in here, so it's bounded as well. So it's bounded in both parts. The RT is bounded in C. Okay, so now we know that it's bounded function in C. What we can do next is this is still mapping. RT is still mapping from C to this, this thing is difficult to handle. Right? So now let's just use the help of the dual space of this Lx. Then for any f in the dual space of this Lx, because this is the Banach space, so I can consider the dual. And then we define a function Wf. So it depends on what this f is, and Wf applied to any number. So the Wf will be going to be a function from C to C. Okay, and what it does is it maps any lambda to Wf of lambda, and it is defined as the value of f of the resolvent at lambda, because the inside here is in Lx, and f is in the dual space, so that's why we get a scalar out of it, and that scalar is it's a complex number in general. Okay, now I have this function, and that is defined here. So on the one hand, I know that the Wf is also analytic. The reason is it is a composition of this analytic function and the linear function, which is really nice, right? So the composition of these two is still analytic. And now it's clear it's analytic in this sense. Right? It's just regular complex valued function. And on the other hand, the Wf is bounded because this is a bounded value, as we showed before. This is always bounded for all the lambda. And then f is applying to some bounded. So f is linear. That's why this is also bounded. So it's analytic and bounded in C. And then by the Cauchy, by the Liouville, again, this is some result from complex analysis. If I have an analytic function, analytic at every point in C, when a function is analytic at every point in C, we call it an entire function. An entire function means that it's analytic at every point in complex plane, and it's bounded. If you have these two conditions, then it implies that the Wf must be a constant function. It is constant function. Constant function means that for any lambda you put from here, it must be a constant function. It must be taking the same value. And we don't know what that value is, but it's a constant value. Okay, so what happens is, it doesn't matter what this lambda is, you always get the same value right here. Okay, and that means this must be a constant. Because if it is not a constant, if say RT of lambda 1 is different from RT of lambda 2, then we know that we can always find some linear functional that can distinguish these 2 points. So that means if this is the case, then there exists some f, which is in Lx star, such that the f of RT lambda 1 is different from f of RT lambda 2. And that means this is not a constant. It takes different values at 2 different points, lambda 1, lambda 2. And that is a contradiction. So this just means that all these are the same. That means RT of lambda is constant and independent of T. Okay, remember what this resolvent is. I don't need that. I just need to see that, say I have this equal to the constant for any lambda. Then let's recall the first resolvent identity, this is equal to mu minus lambda resolvent of lambda resolvent of t, mu. Okay, so they are all taking the same value no matter what the mu lambda mu is. So this is the x from this x is from the space here. Okay, maybe like we call it u. It's constant, and this is the same u, and this is going to be the same u. This is going to be the same u. Okay, so this cancelled. So you just have, then this is non-zero value for different lambda mu. This will be equal non-zero. So that just means that you apply u twice, it is equal to 0. Okay, so that means they all equal to the same u. And remember that each of them should be invertible, right? This should be, remember that this is just the mu I minus t inverse. So each of them is invertible mapping. And they are the same invertible mapping, but they applied twice, you get 0. That is a contradiction. Okay, so that's the contradiction. And that contradiction means that at the very beginning, we cannot say that this is C. The mu of t cannot be the whole complex plan, and that means this cannot be empty set. Okay, so that's where the contradiction is. Okay, now we show that. Let's see how many things we have shown. We show that this rho of t, take the composition of this and this. This is spectrum, and it consists of the 3 parts we had before, right? So we said this is the open. So that means this is the closed. And we also show that if t is the bounded linear functional, then this one here is also non-empty. Okay, and another thing we showed, we didn't specify this, but we showed here that when the lambda, when lambda is bigger than this, we know this exists. And this means that the lambda is in the resolvent. Okay, so what do we mean by that is, if you draw this is a complex plane. We have a circle here which has the radius t. We know that everything outside must be included in rho of t. Okay, must be in the resolvent. Okay, and even something inside could be in the resolvent. The thing is that this thing can only, the spectrum can only live inside this disk, and it's non-empty set. So you could contain at least 1 point in here, but it has to be living inside here. Everything outside must belong to this, must belong to the resolvent set. Okay, so that's what we have shown so far. So it's non-empty, closed, and bounded. And because it's closed and bounded, we know that it's compact, since we're considering the complex set here. So this is a compact set, non-empty compact set. That's what we know. And the very last result we're going to show is to get an even tighter bound on this. And we're going to see how large this set could be. So that means, say I have these points right here. I want to get the smallest circle that includes all the points right here. Okay, that's how we get the tightest bound for this set. Okay, and this radius I just draw is called the spectral radius. Spectral radius. So again, X is Banach space. T is a linear functional. Linear operator. Then the spectral radius of T is denoted by the sigma. The R sigma. R means the radius. Sigma means spectra of T is a real number. And this real number is defined to be the supremum of lambda C and the absolute value of lambda, or magnitude of lambda, or modulo of lambda, such that lambda is in the spectrum of T. Okay, so that's the spectral radius. So the picture is just as I said. We know that the points living in here, but how tight it is. So I want it to be as tight as possible. Say, for example, this one, to include all the points. So the radius here for a smaller circle is called the spectral radius. And the following result tells us the exact value of the spectral radius. It's due to Gelfand. Okay, so what it says is if X is a Banach space, and the T is a bounded linear operator, then the spectral radius of T is equal to the limit of T to the power K norm, and then 1 over K for K going to infinity. Okay, so that's the tightest bound for this spectral radius. Okay, so let's prove this result. Okay, so first, the idea is this. So we try to, let's say I define the notation, just for simplicity, I define R to be the spectral radius I want to estimate. And call L to be the lower limit of this tk 1 over k. I'm going to define U to be the upper limit of this. Okay, so the goal is to show that if the limit exists, then L should be equal to U. And also I want to show that R is equal to these two values. If you can do that, then we can prove this. Right? So that's our goal. So to do this, we first show that R is less than or equal to U. Then I show that R is greater than or equal to U. Then in this case, R will be equal to U. And finally, I want to show that R is less than or equal to L. And then because L is always less than or equal to U, so altogether we can say that these three are the same. Okay, so let's see how do I get to the first one. I'm going to show that R is less than or equal to U. Okay, remember that the resolvent of R of RT at lambda is equal to lambda I minus T inverse, right? And if the lambda is bigger than, so say if lambda has a value bigger than, strictly bigger than the norm of T, we know that in this case, it's like the one here. If it's living in somewhere here, it must be in the resolvent set. So this means that this is invertible and it can be expanded. It's 1 over lambda times, say, I minus T over lambda inverse. And I know that this thing has a norm smaller than 1, so I can take the Newman series, which is sum of T over lambda to the power K. So it's dk, this K. K is from 0 to infinity. And that, I put the lambda inside, which is the tk lambda k plus 1. K is from 0 to positive infinity. Okay? And remember that this actually converges as long as the Cauchy Hamadar. So I said it wrong. It's the Cauchy Hadamard. It's just about the generic power series of complex numbers. It says that if I have a ck zk, look at the power series, which is a function of z, k is from 0 to infinity. The the radius of convergence is converge if the z, the norm of z is less than 1 over the upper limit of the ck 1 over k. K is from 1 to k is going to infinity. So this is called the radius. If it's smaller than this, this is upper limit of the ck to the power 1 over k. Both ck and z are complex values. Okay, so this is the where it converges, and it diverges if z is bigger than that, bigger than this radius, which is again supremum, the same one, upper limit of the ck 1 over k. If it's equal, then it's not sure. It's not sure if it's convergent or divergent, but at least if it's smaller than it's convergent, that's bigger than it's divergent. Okay, so now let's go back to this one. Go back to this one. For it to converge, the 1 over lambda is our z. It's like our z now. You can put the lambda, 1 of the lambda outside, so you still have the same lambda k. But the point is that the radius of convergence is that this needs to be less than or equal to 1 over the upper limit of, now this is like the ck. Okay, if you take the norm, that will be the tk and the 1 over k. So it needs to be less than that. And this is equivalent to saying that this lambda must be greater than the lim sup of tk over k. Okay, so what this says is that as long as your lambda is bigger than this value, which is the u is the upper limit we mentioned earlier, then this is convergent. And this convergent means that this is actually a bounded linear functional, and that means lambda is actually in the resolvent set. So if lambda is greater than or equal to u, then the lambda must be in the resolvent set. And that means it cannot be in the spectrum. Right? This means it cannot be in the spectrum. Okay, and that also means that if you want your, it's bigger than that. So if you are looking for the spectrum, it cannot be in here. It has to be something inside. Okay, so now, previously what we showed is that we know that outside of this with the radius t, it has to be in the resolvent. Now we'll make this even smaller because we get even tighter estimate. This is actually tighter, you can show that. It's even tighter. And this radius is the u. Okay, this radius is the u. Okay, so so from this side we can see that the spectral radius r must be less than or equal to u, because outside of that it has to be it belongs to the resolvent set rho of t. Okay, so that's the first thing we showed. Second thing is that we want to show that r is also greater than or equal to u. Okay, to show this, let's say that for any epsilon greater than 0, in any f in the dual space of Rx, we're going to use the same trick before. We define the mapping Wf, which is a mapping from the rho of t to a complex value. And this is defined as any lambda is mapped to Wf of lambda, and that is defined to be the f of the resolvent at lambda. We know that resolvent exists since that we're picking up lambda from the resolvent set. Okay, so now let's say we have a spectral radius. So we have a spectral radius. We know that it's in here. We don't know what the exact value r is, but I know that if this is spectral radius, then anything outside will belong to the resolvent set. Okay, So that means for any epsilon, R plus epsilon will be inside the resolvent set. So R plus epsilon may be here. Okay, and this in the resolvent set means that I can do this, I can define this WF. Okay, so WF at R plus epsilon, I know that is inside the resolvent set, so I definitely can do this. This is F of RT R plus epsilon. Okay, let's see what this one is. This is just F of the resolvent is lambda, sorry, is R plus epsilon I minus T inverse. Okay, and we showed before that this thing here is equal to the sum, so that when this is lambda, this is equal to T to the power K with lambda to the power K plus 1 for K from 0 to infinity. Now the lambda becomes R plus epsilon to the power K. Okay, and you are applying F to it. And F is just linear, so you just pass it through, and you have the constant below, so it's just F of Tk, and you have R plus epsilon to the power K plus 1, and K is from 0 to infinity. So that's what we have. And we know that this is convergent. Okay, so we know that this is convergent, meaning that for every K, each term is bounded. So there exists, I should say this in so we know that this is a convergent. It should be finite because it's the bounded linear operator. So this will mean that F of Tk for every K, F of Tk over R plus epsilon K plus 1, this thing is bounded. And this is equal to the F, if I put it inside, it's just Tk R plus epsilon K plus 1. This thing is bounded. Okay, this is the bounded value because it's just one term in the convergent series. Well, in this case, you can see this is in Lx, right? And this is in Lx, the dual space of Lx. But I can identify this one with the one in the bidual, just by doing the canonical mapping. I can treat this as something in Lx double dual. Okay, so that's why I can see that this is equal to, if we use the notation before, it's just Tk over R plus epsilon K plus 1 applied to F. So as I said, this you interpret it as in the dual space of Lx, and this is in the bidual. Okay, but this F is arbitrary in here, and this is bounded by some it's finite. So it's finite. Okay, remember that the uniform boundedness theorem says that, so if I have F is a family in, say, the dual space, and for each x in the space X, the F of the supremum of F, I should say F in the family, this F of X is bounded, then that just means that the F is uniformly bounded, right? So the supremum of the F as a norm, F is in F, this is the bounded by some M. This is uniform boundedness theorem. So right now, this is like the X. This is like the X here. And it can be arbitrary from this set. This is my space X. And this is like the X star. Okay? And for each K, I can show that this is bounded. That just means that this thing here is bounded by some M for all the Ks. Okay, so by the uniform boundedness theorem, there exists some M such that the Tk over R plus epsilon K plus 1 is bounded by this M. Okay, so this left-hand side is just the norm of tk over, because it's a positive constant, I just move it outside, it's less than or equal to m. Okay, and then I exchange these two and then take the case root. I'll get r plus epsilon is bigger than or equal to 1 over m to the power 1 over k times this 1 over k. Okay, so now I take the, if this is true for any k, I know that r plus epsilon will be going to be greater than or equal to the supreme upper limit of this. K t 1 over k. But this one always goes to 1 for tk. So that's why this right-hand side is just u. So we show that for any epsilon, r plus epsilon is greater than or equal to u. So that just means r is greater than or equal to u. Okay, so we showed this. And now we showed r less than or equal to u and greater than or equal to u, so the r has to be equal to u. So r equals to u. So to show that it's also equal to L, I just need to show that this r or u is less than or equal to L. And then because u is greater than or equal to L, so I know that they have to be equal. This is the automatic, but I want to show this one on the question if this is true. Okay, so that's the last part. To show this, let's consider the lambda k I minus t to the power k. So just take the case power. Then this, we can rewrite it in the following way. So I'll not show the details, but it's pretty easy to show that you can rewrite this as lambda I minus t times the sum of lambda j minus 1 t to the power k minus j, where j is from 1 to k. Okay, just directly verify that. You just multiply together, then you just get left-hand side. Okay, so I call this the pk lambda t. Okay, but that's just something in Lx. And you can also show that you can switch the two. You can put the pk first, pk lambda t first, and then multiply by lambda I minus t. Okay, you can exchange these two because lambda is just constant, t is the real thing, but you only have the t. You don't have anything that everything's commute. They commute, right? So you have this. So now remember what you have. If lambda k is in the resolvent set of tk, then the lambda k I minus tk inverse exists, seen here. Okay, the inverse exists. That means the lambda I minus t times pk lambda t. You just treat this as the whole thing. It's equal to pk lambda t times lambda I minus t. They commute. And they commute and they are equal to lambda k I minus tk, which is invertible. This one is invertible. So we know that if two operators or two elements in the Bondedness algebra, or this is two operators, if they commute and their product is invertible, then we know that both of them are invertible. Okay, so that means lambda I minus t inverse also exists. Okay, and it's also in Lx. So this means that the lambda is also in rho of t. Okay, so that means rho, if lambda k is in the resolvent set of tk, then lambda must be in the resolvent set of t. Okay, and that also means if lambda is in the spectrum, then the lambda k must be in the spectrum of tk, right? That just means this, because if this is not true, then lambda k will be in the rho of tk. And from there, we will know that the rho lambda is in the rho of t, and that is contradiction to this one. Okay, so that's why we have that. Okay. Now, if lambda is in the spectrum, this is in there, and this just means that we know that with the weakest or the rough estimate we have before is that the spectral radius, sorry, this must be less than or equal to the norm of this, right? Because outside of that, it must be in the resolvent set of TK. So if you're looking at some spectrum, the magnitude must be less than or equal to that. So if this is the case, then the lambda must be less than or equal to tk to the power 1 over k. So if this is true for any k, then the lambda must be less than or equal to the lower limit of this. And this by definition is RL. Okay, so for any lambda in here, it must be less than or equal to L. So that means the spectral radius R must be less than or equal to L. And this completes the proof. As we said, we show that this is also less than or equal to L. And so R must be equal to U must be equal to L. And that just means that the spectral radius is equal to the limit. The limit of this actually exists because the upper limit and lower limit are the same. At the same time, this spectral radius is equal to that. And that completes the proof of Gelfand theorem.